Ideal gas law. In a previous video we examined the concept of an ideal gas, and it had to meet 5 criteria. The key to the concept of an ideal gas is that we can ignore what happens on a microscopic level and simply define quantities on a macroscopic level which define the state of the gas. So the ideal gas law is also referred to as the equation of a state. And there are 4 key macroscopic quantities that we'll need to totally define the gas. That is the gas's pressure, the volume that it occupies, the number of molecules contained within the gas, and the temperature of the gas. And in any equation you need a constant. So we see here that the product of the pressure by the volume is equal to the number of molecules multiplied by the temperature by a constant known as Boltzmann's constant, which is 1.38 by 10 to the minus 23 joules per Kelvin. Pressure is simply force per unit area, and that's in units of newtons per meter squared, or more usefully in atmospheric thermodynamics, in pascals. As we'll see later, the pressure is actually measured in hectopascals, or hundreds of pascals. 1 pascal corresponds to 1 bar of pressure, and 1 hectopascal corresponds to 1 millibar of pressure. And millibars is the units you'll see used in some textbooks. It's the unit favoured by Americans, for example. The volume will be measured in units of meters cubed. The number of molecules is simply a number. And the temperature is always measured or calculated in this equation in degrees Kelvin. Now this equation can be expressed in a way that's slightly more useful for atmospheric thermodynamics. But in order to do that, we need to define a number of quantities. Firstly, we're going to define the universal gas constant, R starred, which is N subscript A, by the Boltzmann constant K. And that's 8,314.3 joules per kilogram per kilomole. We'll define a kilomole shortly. But N subscript A is Avogadro's number, which is the number of which is equal to 6.022 by 10 to the 26 molecules per kilomole. So inversely, therefore, we might define a kilomole of a gas as containing 6.022 by 10 to the 26 molecules. Further, 1 kilomole of a gas has a mass in kilograms equal to its molecular weight, where the molecular weight is the weight of an individual molecule. So the number of kilomoles then, lowercase n, is equal to the number of molecules, uppercase N, divided through by Avogadro's number, N subscript A, but it's also equal to the mass in kilograms divided through by the molecular weight. N equals m on m as the classic equation. So now what we do is we take the equation for an ideal gas, or the equation of state, because it relates various state variables of the gas, PV equals nKT, and the first thing we do is multiply and divide through by Avogadro's number, so that we have 2 expressions here, Na by K and N on Na. Now we've seen that we can define a universal gas constant, and that's Avogadro's number by the Boltzmann constant, so we replace Na by K with R starred. And N, the number of molecules divided through by Avogadro's number, is the definition of a kilomole, N. So we've simplified our equation now, or changed it from PV equals nKT to PV equals R star NT. We then multiply and divide this equation by the molecular weight m, so that we have 2 terms, m, the molecular weight, by n, the number of kilomoles, and R starred, the universal gas constant, divided through by m, the molecular weight. The former term, m by n, is equal to the mass in kilograms of the gas, and we're going to define R starred divided through by the molecular weight as the specific gas constant for a gas with a molecular weight m, and its units are kilograms per kilomole. So our equation is now pressure by volume equals mass of gas by specific gas constant by temperature. If we then take the volume and divide through the entire equation by it, the left-hand side, PV, simply becomes P. And on the right-hand side, we have M, the mass, divided through by the volume, by R by T. And we've already seen that the density is defined as the mass per unit volume. So now we have a more familiar form, pressure equals rho RT. Finally, in meteorology, we're interested in the specific volume, which is the inverse of the density alpha. So divide through both sides of the equation by the density rho, and we have the form that we'll use most of the time now as P alpha equals RT. So P is the pressure typically in pascals when doing calculations. Alpha is the specific volume, which is the volume of 1 kilogram of gas. R is the specific gas constant, and T is the temperature in Kelvin. P alpha equals RT. For dry air, that is air that we considered earlier, that's mostly nitrogen and a small amount of oxygen and other constituents, and contains no water vapor, the mean molecular weight, which you calculate as a weighted sum of the molecular weights of the various constituents, is 28.97 kilograms per kilomole. And so to calculate the gas constant for dry air, the specific gas constant, we take R star, which is 8314.3, and divide through by 28.97, and we get RD is 287 joules per kilogram per Kelvin. And since we'll be using that a lot in this course, it's a number worth memorizing.